So we now have a good working definition of ideal solutions, and I'll remind you that an ideal solution is one that is characterized by having all intermolecular forces basically the same. So it doesn't matter whether it's a force between two particles that are identical or two particles that are not identical. No matter how many components there are, we will say that these forces are all going to be the same strength and the same magnitude. So an ideal solution really won't be distinguishable from either of the pure substances in any substantive way. Now I'm going to consider binary solutions. So we're going to be limited to two components. And I'm also going to make a general, for most of these videos, I'm going to make a general assumption that the second of the two components, P2, has a higher vapor pressure than P1 in the pure substance. Now what this means is that component 2 is the more volatile. So it more easily enters the gas phase for whatever reason. All right, now what I want to do is, with the thermodynamics that we've learned about ideal solutions, and in particular this notion that the enthalpy of mixing doesn't change, so it means that all of those forces are the same, what is the consequence that we have for a solution? And in particular, what I want to focus on is vaporization of the components of the solution. So we want to look at that liquid vapor equilibrium that will exist between the two-component fluid and the two-component vapor. Now, one way to think about this, and let's just draw a fanciful picture. Okay, here's a beaker full of stuff, and this beaker's got a solution in it that's got two different things in the solution. Okay, and these things are dark as I've drawn them here and light that I haven't drawn. Now, if the forces are all the same, let's think about what it takes for one of these particles to enter into the vapor phase. So we need a particle that goes up here and enters into the vapor phase and is now going to be flitting around this solution. All right, it has to break its intermolecular forces with neighboring particles. Well, as long as this is true, that the enthalpy of mixing change doesn't change, so I should have said equals 0. As long as that's true, then it's not any different than that particle being in the pure substance. Okay, but even in the pure substance, it's got to break some kind of intermolecular attraction in order to enter the vapor phase. But that, I guess what I'm trying to say is that's not prejudiced at all by it being part of a solution now, part of a binary solution. All right, so if I'm worried about one particular component, say component 1, and how does it get into the vapor phase? Well, the only thing that limits it really is what is the fraction of component 1 on the surface. Okay, if it's below the surface, we're going to assume that it really can't access the vapor phase. It has to be on the surface, and it has to then get a sufficient amount of energy from neighboring particles to enter into the vapor phase. So if it's not on the surface, it's not going to get there. So I want to look at what is the fraction of each component on the surface. Well, that fraction is simply going to be given by their mole fractions in the solution as a whole. And remember, we're using X to indicate mole fractions in liquid phase and Y to indicate mole fraction in the vapor phase. So I'm really worried about what is the mole fraction in the liquid phase down here, so that it can escape. Well, if this is the case, then one could write a very simple formula for the vapor pressure of component 1. It might just be the mole fraction of 1 times its vapor pressure if it were a pure substance. Okay? If you think about the intermolecular forces for this substance are the same as they are in the solution, so those intermolecular forces are the same, so the only limiting factor is the mole fraction of those molecules. So this, in fact, is our working definition for determining the vapor pressure of a component of an ideal solution. Now, this particular expression is something known as Raoult's law. So I want to write that especially down here so that we can register that this is an expression of Raoult's law. Okay, we would get a very similar expression for the other component as well. So now, if I want to go and revisit the thermodynamics of the solution, recall that we developed an expression for the chemical potential of component 1 in solution is just equal to its chemical potential in the pure liquid, okay, so we'll designate that with a star, plus RT times the log of its vapor pressure for the solution divided by the vapor pressure that it would have over this pure, over its pure substance, over its pure liquid. Okay, but now we have an expression for this quantity here given by Raoult's law. So I can substitute this in there, and you'll notice that the vapor pressure of the pure substance will cancel out when I do that. So this will simply be equal to the vapor pressure, the chemical potential of the pure liquid plus RT times the log of this mole fraction in the solution. All right, so this result, as it turns out, is indicative of an ideal solution. And in fact, it can be shown fairly easily that I could write, if I have this for one of these two components, that I can easily demonstrate that it's true of the other component as well. So in other words, I can assume that both of these things are true. So this is saying that if one of my components, if one component obeys Raoult's law, then both do. Okay, so now that I have an ideal solution, I want to see what this looks like when I look at the vapor phase and when I imagine the total vapor pressure of the solution. So when I do that, I'm going to draw this on a new diagram so I have plenty of space. All right, what I'm going to draw is something that looks like this. I want to draw a diagram that allows my substance to vary from pure substance 1 on one end and pure substance 2 on the other end. So in effect, my horizontal coordinate is going to be the mole fraction of 2 in the solution. I could also think of my mole fraction of 1 as varying from 0 over here to 1 over here if I want, but I'm going to focus on 2 in this case. Okay, so if I were to write the total vapor pressure for my total solution, it's going to have a contribution from 1 as well as from 2. And each of these I can use Raoult's law to indicate that they are simply given by x1 times the vapor pressure of the pure substance 1 plus x2 times the vapor pressure of the pure substance 2. Now I could also use the fact that x1 plus x2 is equal to 1. So x1 is equal to 1 minus x2, and that would allow me to write this total vapor pressure as P1 star plus x2 times the difference between P2 star and P1 star. Now you'll remember that I declared at the beginning I was going to let 2 be the more volatile component. So that means that P2 star is greater than P1 star. So if I draw, this is pure 2 over here, so I'm going to draw P2 star over here, and I'm going to draw P1 star over here, where on the side where I've got pure 1. What I've got here is basically a linear equation, okay? P tot as a function of the mole fraction of 2 is equal to a linear function of x2. So in other words, at x2 equals 0, P tot is equal to P1. At x2 equal to 1, this will cancel with that, this one will cancel with that, and I'll get just P2. So in other words, this will be the graph of my P tot as a function of x2. All right. Now, I could have actually drawn what is P1 as a function of x2, and that would have been something like this. It would have started when x2 is equal to 0, it would have started at its vapor pressure for the pure substance. P2 as a function of x2 would have looked like this. And what I can see is that this total vapor pressure is simply the sum of the two, as I've written it here. All right, in the case of an ideal solution, it will always be a linear graph like this. So that's how you can tell if you've got an ideal solution or not. If it's not ideal, it will vary from, it won't be a linear graph, it'll vary from this graph, and so it won't have this nice, neat appearance. Now, I also want to point out that y1 is equal to x1 times p1 star over p tote. All right, x1 times p1 star is just p1, so this is just the Dalton's law relating the mole fraction in the gas phase to its partial pressure divided by the total pressure. Okay, in this case though, look at this quantity here. P1 star is this point down here, and P tote is all of these points along here. So in other words, P tote is always greater than or equal to P1 star. So that means that this number here is always less than 1, which means that y1 will always be less than or equal to x1. Similarly, I can write y2 is equal to x2 times P2 star over P tote. But since P2 star is always greater than or equal to P tote along here, this number is always greater than 1, so I can always find that y2 is greater than or equal to x2. So what this is demonstrating is that the mole fraction in the gas phase is different than the mole fraction in the solution phase. And in fact, the mole fraction of the more volatile component is greater, and the mole fraction of the less volatile component is less when they enter the gas phase.